So today we are going to learn a new section, section 4.3, solve the type of differential equation by multiplying through an equation by an integrating factor. Okay, so let's do a revision. So in the previous two sections, we learned two types of differential equations. So the first one, we can use separating variables method. Okay, so the corresponding type is like this. So you may think that whether we can use separating variables method to solve it. And if we can, okay, so for example, if you come across an equation like in type 2, okay, section 4.2, so you may check whether the left-hand side or one side can be written as a derivative of a product. Okay, if we can, so we will use the way introduced in section 4.2. Okay, so these are the two types we learned in the previous two sections, and today in section 4.3, we learn a new kind of differential equation, and the pattern looks like this. Okay, so you may check whether we can use the previous two, methods to solve this equation. And if we can, we have to find a new method. And you see that in type 2 and type 3, the two equations looks very similar. Okay, very similar. So maybe they have relationship. Okay, and now let's look at an example 6. Okay, so look at this equation. So you see that this equation looks like type 2. Okay, looks like type 2, but however, we cannot write the left-hand side as a derivative of a product because the two functions here, it is, if we write, okay, so here one is y and here it is 1 only. Okay, so if we d1 times y, it is just dy by dx only. Okay, we can not find two terms. Okay, we cannot find two terms, but however, if we multiply x cubed, on both sides, so we can have x cubed times dy by dx plus 3x squared y equals sine x. And now we multiply x cubed on both sides. You can see that the left-hand side now can be written as a derivative of a product. Okay, so it can be written as dx cubed times y by dx equals sine x. Okay, and then we multiply dx on both sides, so it will be and then we integrate the equation on both sides. And finally, we can get x cubed y equals negative cosine x and then plus constant c. Okay, cosine x. Okay, so finally y just equals negative 1 over x cubed times cosine x plus c over x cubed. Okay, so just now in solving this differential equation in example 6, you see that we multiply. Okay, so if we multiply a suitable factor on both sides, we can write one side as a derivative of a product, which means it becomes the type in section 4.2, okay? So it means that if we come across a differential equation which does not belong to type 2 and also it doesn't belong to type 1, so if it looks like type 2 and we can multiply a very suitable factor on both sides and make it to be type 2, okay? So now we are going to find, okay, we are going to find the suitable factor. Okay, so what the suitable factor looks like, okay? So now let's look at the general equation, the general type, okay? So now let's see. So suppose f of x is the suitable factor, okay? So if it is a suitable factor, it means that if we multiply fx on both sides, so fx times dy by dx plus px and fxy equals fx times qx, and this equation will become, okay, so now we multiply a suitable factor, it becomes the type in section 4.2, okay, so this becomes the type in section 4.2, okay, so it means that, which means that this side, the left hand side, can be written as a product, a derivative of a product, okay? So here let's look at the two functions, okay? So one of it is y and another one should be f, okay? So here is dy and we keep f, okay? So later we will df and then keep y, you see? Okay, so we can write as dfx times y by dx equals f of x and qx, okay? And now again, if we simplify it again using the product rule, so it becomes fx times dy by dx plus df. df, it is the derivative of fx, okay? And then keep y equals fx times qx, okay? So now let's look at equation 1 and equation 2. So actually these two equations should be the same, okay, should be the same, because if in equation 1 we just multiply fx on both sides and it becomes the type of the question in section 4.2, which means that it can be written as the derivative of a product. And if we use product rule to simplify it, and it becomes like this pattern, okay? So it means that equation 1 and equation 2 are the same. So by comparing, you see that, we can get, you see, obviously, this color, okay, you see f of x, the derivative of fx should be equal to px times fx, okay? So by comparing, we can get px times fx equals f prime, okay, f prime. And then if we write f prime as dfx by dx, and then we have this pattern, okay? And we simplify again. So I multiply dx on both sides and divide fx to the left hand side. It will be 1 over fx times dfx equals px dx. And then now if we do integration on both sides, And now look at the left-hand side. So left-hand side, actually, you can regard it as integrate 1 over u du. Okay, so if you regard fx is u, so it will be the integral of 1 over u, the indefinite integral of 1 over u. Okay, so it means that the left-hand side can be written as ln absolute value of fx equals the indefinite integral of px. All right, so now it will be very easy to find fx, the suitable factor. Okay, so by the definition of ln, so the absolute value of fx equals e to the power of the indefinite integral of px. Okay, so fx can be e to the power of the positive one. Okay, so e to the power of the indefinite integral of px, or maybe fx can be the negative one. Okay, however, no matter which one you choose, and both of them are the suitable factor that can make the original equation to be the type in section 4.2. Okay, in section 4.2. So inconvenience. Okay, inconvenience. So we choose fx to be the positive one only. Okay, so we don't choose the negative one. But if you like, you can choose the negative one. So if you multiply this on both sides of the equation, actually, finally, the negative side will be cancelled also by multiplying -1. Okay, so actually, finally, we just choose this one. Okay, so now we find the suitable factor. So the suitable factor is like this. Okay, so it means that when you come across an equation, a differential equation like this, dy by dx plus px times y equals qx. Firstly, you may think whether we can use the way in section 4.1, okay? And if it can. So we will use the way in section 4.2. And if it can't also, and we will try the way in section 4.3. Okay, so you have to identify what is px here. Okay, so actually px should be can be regarded as the coefficient of y. Okay, of y. Okay, so now let's look at an example. Okay, example. So let's look at example. Let's do a conclusion first. Okay, so conclusion is that when you we have done just now. So when you come across a differential equation like this, dy by dx plus p of x times y equals qx, and then if you multiply a suitable factor e to the power of p, the indefinite integral of px, and then like this, so e to the power of px, the integral of px times dy by dx plus e to the power of the indefinite integral of px, and then px times y equals e to the power of the indefinite integral of px times qx, and then this equation will become the type in section 4.2, which means that one side can be written as a product, the derivative of a product. Okay, so now let's look at example 8. Okay, example 8. So example A, let's see. So obviously, for this equation, we cannot use the way in section 4.1 separating variable method. And section 4.2, for section 4.2, we cannot also, okay, because you see the original function is y, and another one is 1 here, okay? But if you d 1 times y, we cannot get these two terms, okay? We cannot get these two terms. So it means that we should find, okay? We should find a suitable factor, okay? A suitable factor. So the suitable factor is called integrating factor, okay? Because you see the factor includes integration, okay? Integration. All right, so now we are going to find the suitable factor. So look at this equation, okay? So you see that we should check this equation with the general format, okay? General format is this one, okay? So it is dy by dx, and then plus, okay? So plus here is y, so it means that px is negative 4. So firstly, we should find px, which is negative 4, and qx is e to the power of x, but actually we may not use qx here, okay? But we should use px, so you have to identify px. So px is negative 4, and then the integrating, okay? So the suitable factor is also called integrating factor, okay? Right here. Integrating factor, okay? So later we will call it integrating factor, okay? So this is a formal way, okay, to call the factor, okay? So integrating factor. So the integrating factor is e to the power of the integral of px, so which is we integrate negative 4, okay? And then it equals e to the power of negative 4x, okay? So here we don't need a constant c here, okay? Why we don't need a constant c? Because if you write constant c, okay, but actually you see it becomes e to the power of negative 4x times e to the power of c. So e to the power of c is a constant. If you multiply a constant on both sides, finally we can cancel the common factor, okay? So constant term will not help us in this way, okay? So we just choose, okay? We just choose the main part, okay? So here we don't need the constant term here, okay? So now we find the integrating factor, and then now we multiply the integrating factor on both sides, so we can get so the next step will be e to the power of negative 4x times dy by dx minus e to the power of negative 4x times 4, here is 4y equals e to the power of negative 4x times e to the power of x, which will be e to the power of negative 3x, okay? So now, after multiplying the integrating factor, so the left-hand side can be written as a derivative of a product. So it will be d e to the power of negative 4x times y by dx. You can check whether it is true or not, okay? So actually it is true. Dy and keep e to the power of negative 4x, okay? And then d e to the power of negative 4x, which will be negative 4, okay? E to the power of negative 4x, so it is true. So equals e to the power of negative 3x, all right? So now we can write as d e to the power of negative 4x y equals e to the power of negative 3x dx, okay? And after that, we do integration on both sides. So we will get integrate 1 e to the power of d e to the power of negative 4x y equals the indefinite integral of e to the power of negative 3x dx. Okay, so now it will be very easy to find the answer. So it is e to the power of negative 4x times y equals e to the power of negative 3x, but we should multiply 1 over negative 3 to adjust it, okay, and then plus constant c, okay, plus constant c. So finally, we can simplify the answer, okay. So finally, y just equals, here is e to the power of negative 4x, okay, negative 4x. So finally, we multiply e to the power of negative 4x on both sides. So here, multiply e to the power of negative 4x, okay. So from this step, we multiply e to the power of 4x on both sides. So we can get y just equals e to the power of, it will be negative, okay, negative 1 over 3 e to the power of x, and then plus c times e to the power of 4x, okay. So this is the solution of example 8, okay.